All right, here we are in the third part of my three-part groundwater series. And we're going to talk about mining groundwater. So, mining groundwater is just water extraction through wells. And what's important about this is we talked about in the first video how groundwater resources account for less than 1% of all of the hydrosphere, right? So, really, we should consider groundwater to be a non-renewable resource. I realize that terminology suggests that eventually we'll have none of this water left. So that's not entirely accurate. However, at the amount or the rate that we withdraw water from wells drilled into aquifers, we are taking more out than can be replenished naturally by seasonal rainfall, right? So in other words, our discharge, our extraction exceeds our recharge, which is rainfall or precipitation. And a great example of where this is happening right now is in the central United States, something called the Ogallala or High Plains Aquifer. So let me show you what that looks like. Obviously, this is a map of the central United States, but what you're seeing here in the rainbow of colors is groundwater, and the groundwater is represented by depth. So you can look at the colors indicating where the water table has dropped more than 150 feet in recent years compared to, and that would be in red, where the water table has risen about 50 feet, and that would be in blue. So there's really only one area up here by the Platte River in southern Nebraska where the water table has increased in its height rather than dropped in its depth. So what that means is that during the past 60 years or so, there's been a rate of withdrawal of this groundwater that has by far and away exceeded the amount of recharge from precipitation. So the water table is dropping at a rate where it's not going to be present much longer, and especially these areas in here. Okay, it's taken about 5 million years to fill this reservoir. So this area, this aquifer, is made of very porous sandstone that again acts like a sponge, and because of its high porosity, it's excellent for storing water. But if we are using too much of that water through pumping and irrigation and domestic and industrial use, then we're going to see a lowering of the water table that affects a huge area of our bread belt. Okay, so not only are we pulling all of this water up and out, but what happens is the ground beneath these areas that was saturated with water is now not. And so the fact that the sediment is separated by a pore space that's not water makes it really unconsolidated, and it causes areas that are heavily pumped to subside or sink. For example, in Central California, this is kind of scary. The aquifer there that's used primarily for irrigation in wine country has caused the ground to subside about 9 meters, meaning like literally it's dropped the surface of the earth in California by 9 meters. Other examples of where there's been greater discharge than recharge would be Arizona, Nevada, Las Vegas, New Orleans. These are all heavily populated areas that rely on groundwater for municipal use. And unfortunately, they extract way too much water from these areas. And so you can kind of see here in the San Joaquin Valley where the land was back in 1925, and then 50 some years later, in 1977, more than 9 meters drop. And I would argue that today in 2020, it's even more than that. So this can create situations where you get sinkholes and other really scary geologic events. Another thing that is cause for concern is when we're pumping water out of these wells, if this is happening close to coastal areas, we can cause something called saltwater intrusion. So fresh water is less dense than salt water, right? And as you extract the fresh water on the surface of our aquifer, and here's a cross section where you can see that, what happens is as we're pumping water up and out of these wells, the less dense fresh water is the first to go. And what that does is it allows for groundwater that's salty to infiltrate and then contaminate your wells. So you don't want to get salt water pumped out of your well that you're using for domestic purposes, right? So excessive pumping can cause this saltwater contamination. Another big issue we're going to talk about this week is contamination of groundwater. And one common source of contamination is sewage. Obviously the sewers, run under the surface like driveways and roadways and all of that. And those sewers can leach into aquifers and can contaminate groundwater that could travel over vast areas if not treated, right? So not only are sewers a source, but septic tanks. I don't know if you know any people that live in rural areas, they might have a septic tank for all of their human waste. And what can happen is over time, these septic tanks can leak or crack. And that contaminated water can seep down through cracks or pores into the water table and then be carried for months or years following the surface topography down gradient and contaminating wells and areas close to the original source. So we call that point source pollution because we know exactly where the pollution originated here in the septic tank. And that contamination can travel within the entire aquifer, which can be really scary. Other sources for contamination of wells could include like salts that we use to treat roadways in the winter, fertilizers and pesticides, and herbicides. This is particularly true in agricultural areas like Ohio. So we have lots of farms in Ohio, and those farms use fertilizers and pesticides and herbicides to keep all the nasties away. And unfortunately, these fertilizers and pesticides and herbicides can contaminate groundwater. It can lead to a lot of problems that we'll explore when we talk about surface water too. So we don't want these chemicals leaching into our groundwater supply. Here's a landfill on the left. Landfills obviously are full of lots of chemicals and non-biodegradable things that can cause problems with our water supplies. Over here on the other side, we've got a lead pipe. If you were kind of following current events over the last 5 years or so, Flint, Michigan's been dealing with contamination from lead-based pipes that cause a whole heck of a lot of economic and health and all sorts of problems, okay? In addition to contamination, groundwater can erode rock or dissolve it. And this is something we see in Ohio. It's also something that we see in parts of the southeastern United States where water will interact with limestone and actually dissolve the limestone. And when it dissolves the limestone, what it does is basically creates kind of cavernous areas beneath the surface. So you guys have seen pictures of these caves. There's a really sweet virtual tour of, I think it's Carlsbad Caverns, that I posted in the groundwater unit. But you might watch that because it's pretty cool. A lot of the water that's eroding this limestone creates sweet formations underground. Mammoth Cave is in Kentucky. Carlsbad is in the southwestern U.S. And these caverns develop as groundwater dissolves limestone and recrystallizes deposits of calcium carbonate in the form of something we call stalactites and stalagmites that look like this. So we can thank groundwater for the creation of these beautiful landforms. And also a terrain that's unlike any other. We call it karst topography. And this would be a relic of dissolution of limestone by groundwater. And so it creates cavernous underground areas. It can cause sinkholes to form where the surface subsides. We see a lot of those sinkholes in Lake Florida, which is primarily limestone bedrock. So it creates a really interesting topography that you'll investigate in lab number 10. So I'll leave you with that. Lab number 10 is due Friday by 11:59 p.m. And it's all about groundwater. So read the introduction, answer the questions to all the exercises, and upload on Schoology at your earliest convenience. On Friday, I'm going to introduce our next lesson, which is going to be a current event application of groundwater and surface water. So stay tuned. Bye for now.